Welcome to the lectures on electromagnetic fields. Today we discuss lecture number 5.1 from Unit 5. I'm Dr. Srikanth from Gayatri Vidya Parishad College of Engineering. So, the topics that we have in the fifth unit are basically Faraday's law of electromagnetic induction in integral and point forms, Maxwell's fourth equation, statically and dynamically induced EMF, modification of Maxwell's equations for time varying fields, displacement current, pointing theorem, and pointing vector. The course objective 5 for this particular course is to understand the concepts of displacement current and pointing theorem and pointing vector. So, if we first review our previous discussions from electrostatics and magnetostatics, the integral form we have understood from the Gauss law that integral over the closed part d dot ds equal to q enclosed and integral b dot ds equal to 0, integral E dot dl equal to 0 and integral H dot dl equal to I enclosed based on Ampere's law, Biot-Savart's law, and Gauss law. So once we have this discussion, we have also seen the same laws in differential form like del dot D equal to rho v from the Gauss law, del dot B equal to 0, del cross E equal to 0, del cross H equal to 0 from the Ampere's law. Now, the basic motivation of our studies in electrostatics and magnetostatics was to understand advanced machinery. So the discussion has to go from the time invariant domain to the time varying fields. Earlier, the discussion was pertaining to the electric field and magnetic fields with the XYZ coordinates, which are like dependent on the stationary charges or dependent on the steady current. But if we are taking the time varying field, we would have to include a parameter time t, which is making us to consider the electric field in terms of the moving charges in the magnetic field by considering varying currents. This is a basic difference on the way we analyze these particular time varying fields and the time invariant fields. The static fields will not have the time parameter which we include in the time varying fields. So some examples of the time varying waveforms are like the sinusoidal, the sawtooth, and the pulse as I've shown here. Here we can understand these are time varying examples which we need to analyze. As we proceed with the first concept, we have to understand the major contribution have to be understood from Michael Faraday. Michael Faraday was an English chemist and physicist, known for his pioneering experiments in electricity and magnetism. He studied the nature of electricity. Later in his life, he became a professor of chemistry at the Royal Institution. He discovered benzene and formulated the second law of electrolysis. Then Faraday's greatest contribution to science was in the field of electricity. As such, Faraday introduced the concept of lines of force. It was initially rejected by most of the mathematical physicists of Europe. He discovered electromagnetic induction, which is covered in this particular chapter, and the battery, the electric arc, plasmas, and the Faraday cage based on electrostatics. His biggest breakthrough was the invention of the electromotor in the dynamo or the generator, which depends on the Faraday's law of electromagnetic induction. So here we have to remember what Faraday has done. Basically, Michael Faraday observed that an electromotive force, EMF, was induced in a wire loop when a permanent magnet moved near the loop or the loop moved near the magnet. So you can see here the displacement in the gray shade, in the blue shade, in figure A, where we can see the displacement of the magnet near the loop. And then in the second case, where the loop has moved and the magnet is static. So here you can say that an electromotive force, EMF, was induced in the wire loop when a permanent magnet moved near the loop or the loop moved near the magnet. Okay. The electromotive force is nothing but a voltage induced in the loop. Faraday's law of electromagnetic induction states that the induced EMF in a wire loop is equal to the negative time rate of change of the magnetic flux linkage within the loop. So here the wordings are slightly different with the different authors, but basically it would confine to the induced EMF equation mathematically. In terms of the fields, we know, so they say that a time-varying magnetic field produces an electromotive force, EMF, that may establish a current in a suitable closed circuit. An electromotive force is mainly a voltage that arises from conductors moving in a magnetic field or from changing magnetic field, and we shall define in this section. Faraday's law as such is customarily stated in mathematical terms as EMF equal to minus d phi by dt, or rate of change of flux nodes. Okay, so when we say this, above equation implies a closed path, although not necessarily a closed conducting path. The closed path, for example, might include a capacitor, or it might be a purely imaginary line in space. Magnetic flux is a flux which passes through in and every surface whose perimeter is in the closed path, and d phi by dt is the time rate of change of this flux. And here, we also have to remember another important law, which is the Lenz's law. The direction in which the induced EMF drives current around a while loop can be found through the negative sign. However, it is usually easier to determine this direction with Lenz's law, named in honor of its discoverer Heinrich Lenz, who, who happens to state that the direction of the induced EMF drives current around a wire loop to always oppose the change in magnetic flux that causes the EMF. A non-zero value of d phi by dt may result from any of the following situation. One, a time-changing flux linking a stationary closed path, a relative motion between a steady flux and a closed path, or a combination of the two. These three different scenarios based on which we can study statically induced EMF, dynamically induced EMF, and the scenarios will be discussed in the later lectures. So here it is important to understand that this particular Faraday's law as such plays a crucial role in the working principles of various generators and as such our motors. One of the important things that we have to remember from the Faraday's law of electromagnetic induction is how we derive the Maxwell's equation, which again are very crucial to understand the operation of various electromechanical devices or systems. So according to Faraday's law, we have our electromotive force equal to integral of closed path integral E dot dl, which is equal to minus d phi by dt. But we also know the flux can be defined in terms of the flux density as integral B dot ds. So rewriting these equations, integral E dot dl equal to minus d by dt of integral B dot ds, or integral E dot dl equal to minus integral dou by dot ds. So the electromotive force around a closed path is equal to the time derivative of the magnetic displacement through any surface bounded by the path, based on Stokes' theorem, which tells integral A dot dl equal to integral del cross A dot ds, which basically correlates the line integral to the surface integral, where A is any vector. We can understand that integral E dot dl can be rewritten as surface integral of del cross E dot ds, or del cross d E dot ds equal to minus integral dou v by dou t dot ds, so which basically results in our Maxwell's fourth equation, which says for the time varying fields, del cross E equal to minus dou v by dou t, which is nothing but the rate change of flux density. Here, this being an important equation is primarily required for solving many of the numerical problems in both theory and from the exam point of view, and also from the practical experimental viewpoint. So if we take the example of a problem here, given the magnetic flux density B bar equal to 6 cos 10 power 60 sine 0.01 x AZ, millitesla, find the magnetic flux passing through the surface z equal to 0, 0 less than x less than 20, 0 less than y less than 3 at t equal to 1 microsecond. The value of the closed line integral of E bar around the perimeter of the surface specified above at t equal to 1 microsecond. So given the flux density, and if we are asked the surface detail, the magnetic flux passing through is to be determined. And then we are also trying to find the line integral of E bar. Here, a basic solution can be obtained by considering phi equal to integral B dot ds. So for the surface z equal to 0 plus or minus az is perpendicular. Hence ds bar would be something like plus or minus dx dy. Is that basically the surface that we are considering? As plus az bar is present in B bar, ds will be plus ds dy az bar. Hence phi will be, if you are taking based on what is given for B bar, 6 cos 10 power 60 sine 0.01 x az dot dx dy is that into 10 power minus 3. So taking the integral limits between 0 to 20 and 0 to 3, we end up getting this value to be 0.03588 cos 10 power 60. At 1 microseconds, that would be something yielding as a value of phi equal to 19.3x milliweber. So this is the basic simple problem which normally we encounter when we are trying to understand this particular aspects of Faraday's law. Then the second part of this particular question as the EMF integral E dot dl equal to minus dou v by dou t dot ds. So we again substitute the given parameters and then we try to analyze the values here. Then we see that EMF equal to integral 0 to 20, 0 to 3, 6 into 10 power 3, sine 10 power 60, sine 0.01x dx dy. So which yields us this particular value of 35880.15988 sine 10 power 60, which again is evaluated at 1 microsecond as per the given data. So we end up getting integral E dot dl equal to 30.192 kilovolts. So this is a very interesting problem, which normally is the kind of problem that we encounter in this particular course. Similarly, we have another problem. This I have drafted from UA Bakshi. So we have a circular loop conductor which lies in the plane z equals 0 and has the radius of 0.1 meters and resistance of 5 ohms. Given b bar equal to 0.2 sine 10 power 3 t az, let's determine the current in the loop. So here a circular loop is in z equal to 0 plane, b bar is in z direction as given, which is perpendicular to the loop. So b bar is perpendicular to circular loop. So what will be like the total flux? Okay, so the total flux is integral b dot ds. And then with cylindrical coordinate system, ds bar equal to r dr d phi az. So phi equal to 0 to 2 pi, r equal to 0 to 0.1, which are the limits based on the given problem. And then we integrate this particular within the limits, our b bar, which is given with the dot r dr d phi az. So if you evaluate this value, this would end up to a value of 6.283 sine 10 power 3 t milliweber. Now induced EMF is nothing but E equal to minus d phi by dt, or minus d by dt into 6 d by dt of 6 by 2.83 into 10 power minus 3 sine 10 power 3 t. So that gives you the cosine function minus 6.283 cos 10 power 3 t volts. Okay. And then basically, if we see at the question again, we are asked to determine the current in the loop. So as a result, the current in the conductor is given by I equal to induced EMF by resistance, which gives you minus 1.2567 cos 10 power 3 t amps. So this is another typical problem that we encounter with this kind of concept. So going forward, we can understand that two important things that we have understood in this particular lecture, and we are talking about the differential form or the integral form of electric field in static environments. So we have like del cross E equal to 0 or integral E dot D equal to 0, which when reflected into the time varying fields would change as del cross E equal to minus dou B by dou T, or integral E dot dl equal to double integral of dou B by dou T dot ds. So this is a basic difference between the static fields and the time varying fields, which we have understood in this particular lecture. So when we have what we have basically discussed in this lecture is how time varying fields are different from static fields. What is Faraday's law of electromagnetic induction? How to derive Maxwell's equation from the Faraday's law? This is a basic concept that we have covered in this particular lecture session. Then typically there will be objective questions in various competitive exams, something which appear like this. When a conductor cut magnetic flux, an EMF is induced in the conductor. Above statement is based on what law? Is it Faraday's law, Coulomb's law, Ampere's law, or Joule's law? So basically we should be able to indicate the statement and remember the Faraday's law statement. Similarly, as the second question, as you can see here, a straight conductor of finite length moves at right angles to its axis at a velocity in a uniform magnetic field. Then the EMF induced the conductor is maximum. The direction in which the conductor moves is parallel to the field, perpendicular to the field, at 45 degrees to the orientation of the field, none of the above. Again, the direction of each of the magnetic field and the electric field, or if we are taking the direction of the current, reflective of each other, should be importantly observed. And the last question here, you can understand the Maxwell's equation derived from Faraday's law in the point form is del cross E equal to minus dou B by dou T, del dot E equal to rho by epsilon, del cross H equal to J plus dou D by dou T, del dot B equal to 0. So basic remembrance of the equations is very important, because in the competitive exams, you should be able to answer this question without looking into the other equations or deriving it by just memorizing the basic Maxwell's equations. Now, typical questions that appear in examinations for the theory part would appear something like write expressions for Maxwell's fourth equation in integral and point form, discuss about Faraday's law of electromagnetic induction in detail. So these are some of my references for this lecture, like the J.D. Cross, we have Sadiq Kulkarni, and then William Haight, and then Bakshi, some of the references. Thank you.